Recursion is probably my favorite topic to teach first year, because it shows you something you already know, but you think about it in an entirely different way. Because it's how we do, how we repeat instructions. But we've been doing that with loops, but we can do it with recursion. And in fact, if you go back, I don't know how long ago, back in the 40s, I don't know. And you look at the original formulation of programming and how it's defined, how it's modeled. There's Alan Turing's approach, and then Alonzo Church, I don't remember his first name. Someone look up Church-Turing thesis and tell me the name of the other guy. I think it's Alonzo? So someone confirm that they're doing that for me right now. Okay, yeah, let me know. And then there's Church from Princeton. Alonzo, I was right, nice. From Princeton. Oh, no. But so Turing's model and Church's model of computing came out around the same time-ish. And they're effectively equivalent to one another. Effectively, they are equivalent to one another. But they're done very differently. And Church's was all recursion-y. But Turing's was all loopy, let's say. I'm explaining this very poorly, of course, but that's kind of the idea. So, although we're talking about looping, this actually kind of works towards a different formulation of computing a little bit. They're equivalent. In anything you do with one, you could do with the other. And I find it so interesting to teach recursion because it's looking at the flip side. You're looking at the world in an entirely different perspective, but it's equivalent. So it's really interesting to me. And a lot of people get weirded out when they learn recursion the first time, but I think that's only because you're used to loops. I could have started you with recursion and we never talked about loops, and you'd probably be weirded out by loops. So try not to let the fact that you're comfortable with loops get in the way of recursion. And I also think a lot of people get weirded out by recursion because they're told that it's weird and it throws them off and it's confusing and it's hard to understand. I don't buy that. I think if you're here, you are fully capable of understanding this completely. So try not to let what other people have told you about recursion throw you off if people have kind of spooked you a bit. But recursion is just repeating the same chunk of code over and over and over and over again. When something is recursively defined, though, it means that something is defined in terms of itself. Which sounds a little strange, but you're already all pretty familiar with this idea, whether you like it or not. But before we get to that, I'm going to start with an example of counting some people recursively. And I did this example in labs, so maybe you've seen this example before because I may have shown it to you, but if not, I'm going to do it again now anyways. But I've got a line up here. And I want to know how many people are in that line. So what do? I go, okay, well, I count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Looks like there's 14. Did other people count 14? You didn't count? Well, looks like there's 14. But I did that very iteratively. But I'm lazy. I don't want to count everything. So here's what I'm going to actually do. I'm going to ask the first person in that line over here, how many people are there in that line? I'm only going to ask one person. And they're going to tell me. But the trouble is that one person doesn't actually have the answer to the question yet. They're going to get the answer to the question. Because that one person at the front of the line goes, well, the total number of people in this line is however many people there are after them plus themselves, right? So if the person at the front of the line happened to know how many people are after him, they just add 1, and then tell me. So if there are X people behind him, then he just tells me, well, there's X plus 1 people. Right? Does that make sense? If they magically knew how many people were behind them, they just need to add 1 to it. Right? If this is throwing you off, you're thinking way too hard. Cool? So here's what they're going to do. They're going to turn around and say, hey, person with your mouth open, how many people are there in this line? And they're going to go, oh, I don't know. But I know it's the number of people behind me plus 1. So what are they going to do? They're going to ask the person behind them and say, how many people are there in the line like here? So every time I ask this person, and then they know it's all of these people plus them. They're going to ask them, and this person is going to tell this person it's all of these remaining people plus them. And they're going to ask them, and they're going to say, well, it's all of these people plus them. So far, so good? Eventually, we keep doing this, and we're going to get to this person here. This last one, the smiley one, if you can't tell, the picture's repeating. I was lazy. There's not 14 unique. There's 4? Is that 1, 2, 3, 4? Yeah, that's right.
No, that's 5.
1, 2, 3, 4, 5. Well, there's however many there are. I'm going to get to this the second last person. And they have to tell the person that asked them, who was this one, how many people there are. And they know, well, it's me plus the one before. Or the one before, all of the ones before. So they're going to ask the person at the end of the line. And the person at the end of the line is going to be asked the question, how many people are there? And they're going to say, well, it's however many behind me. Oh, there's none. There's no one behind me. So how many people are there? 0 plus, oh, it's just me. So they tell the person in front of them there was 1. And they go, oh, well, it's 1 plus me, that's 2. And then they tell the person in front of them. Let's do this example in this row right here. Okay? How many people are in this row? Well, you plus, so you can't tell me yet until you know their answer. So ask them. You don't know. So you better find out. He's got to know. Ask him. I don't know if he's paying attention. Nope. Let's try again. Your row's cut. We're going to you. How many people in the line? Well, hold on. Look over there.
Okay, and the base case is no.
All right, so there's no one. 1. So now I know there's 5. No one person did all the work, though. The total amount of work was actually like delegated along the way. And notice that in order to answer the question, I asked you a question, but you couldn't answer the question until you asked them a question and their answer was given back. But they couldn't answer the question until they asked them a question and their answer was given back. So in order to answer the question, we had to go like all the way down and then back up, which is kind of neat. Kind of, yeah. Any questions so far? No, this is just the idea I'm giving you, okay? So iterative definition of something versus a recursive definition. Now, it might feel like some of these examples are contrived, and I suppose they kind of are, but they're real examples. There's nothing wrong with them. So a group of people, let's say there's a group of people, like the line of people above. It may seem like a silly question because it's so intuitive. But if I were to say, what constitutes a group of people? You could say like, well, 2 people or 3 people or 4 people or 5 people, you know, whatever. 2 or more people, right? But that's a very like iterative definition of something. we could define a group of people in terms of itself, rather succinctly. So a group of people is two people, or if you have a group of people plus one more person, it's still a group of people. So if I asked you the question, is two people a group of people? It's really easy for you to answer this because of those two parts of the definition of what a group of people is, two people or a group of people plus one more person. Is two people a group of people? Yes. Why? Because it said right there, two people. Two people is a group of people. By definition, it's just there. It's spelled out for me. It's the first part of the recursive definition. But that part of the recursive definition isn't the particularly interesting one. The second part of the definition is more interesting because that is the actual recursive part. Because remember how I said something's recursive if it defines itself in terms of itself. See how a group of people is defined by using the definition of what a group of people is? It's kind of weird, right? But yet this actually makes complete sense. If I ask you if four people are a group of people, you look at that definition and you go, well, now I don't know. Because it's not listed there yet. But I know that two people is a group of people. And if two people is a group of people, and I add one more to it, I have three people. And the second part of the definition says that that is also a group of people. I'm going to get tongue-tied a lot, I think. And then if three people is a group of people and I add one more to it, that's still a group of people by the second part of the definition. So four people is in fact a group of people. I could go the other way because I kind of went from the bottom up, but I could actually kind of go down where I could say, okay, is four people a group of people? Well, in order to know if four people is a group of people, I need to know if three people is a group of people. And in order to know if three people is a group of people, I need to know if two is a group of people. Two is a group of people by the definition, which means three is a group of people, which means four is a group of people. So we kind of answered it in two different directions there, for lack of a better term. One, we started at like the base case, this is the word you were using. And the other one, we started at the recursive case and worked towards the base case. Both make sense. Any questions? Yes?
Is that like induction?
So, if you raise your hand if you've learned about induction before. Two people. Do you, okay, four people, good. I feel better. But I swear to God, I learned induction in high school. What do they teach kids these days? Not induction, yeah, that's not much, I guess. Maybe I'm misremembering. I'm pretty sure I remember learning induction in high school, yeah.
Like induction, like electricity?
No, not inducing, no. Proof, it's like how you prove things in math by induction. You always use K. And then you go for like the, anyways. So for those of you that know, if you don't know what induction is, it doesn't matter at all. For those of you that do know what induction is, yes, you're absolutely right. It does seem a hell of a lot like induction, doesn't it? Yeah. All right, so the base case is something that has a very clear definition, and the recursive case is one that defines something in terms of itself. Now, here's a warning. I like to include these. So there's nothing saying that your recursive stuff has to have a base case, or only one base case, or whatever. This is like, in general, this is what you're going to do. You're going to have your base case and your recursive case, typically in general. You could have more than one base case. You could have more than one recursive case. But this is like your most general, basic form of recursion. There are going to be exceptions to these rules. Usually not having a base case is a recipe for disaster. Usually having, as soon as you start having different potential recursive calls, that's just a nightmare to keep track of. Like, it's entirely possible. But I'm just speaking in this, like, in general, hey, we're learning about this. Of course, we could break these rules however we want. Remember the O example I showed you? But it created that stack overflow. Well, that's an example when we didn't have a base case, when we didn't have like a stopping point, like a concrete point, yeah.
If you have an algorithm though, wouldn't it be like unprovable to be like valid without a base case?
Unprovable? I don't know.
Because like, or at least to prove it like by induction, you would need a base case.
I don't know if you'd have to do proof by induction. I don't know. I don't actually have the answer to that question. It's an interesting question, but I do not know. So for the purpose of our course, we're always going to have a base case. Now that was an algorithmic definition of something. Like, or I guess it wasn't even really an algorithm, but you know, when we were defining a group of people, like the process in which we described whether or not we had a group of people was very like algorithmy, right? But we could define data structures recursively, like a list, right? Or linear linked structure, whatever. But you can think of the lists in Python or the bags in Java that we wrote. A base case is an empty list, okay? We're going to define a list recursively. An empty list is the base case. We have a list. It is a list, but there's nothing in it. Not to be confused with, well, an empty list is just nothing. No, an empty list is a list with nothing in it. Very important to mind the difference. And the recursive case is, well, there is a head of the list, the beginning, followed by the tail, which is everything else. The remaining portion of the list. So, for example, if you consider this little exists there, A, B, C, D, E, we can break this list down into the head, A, and the tail, which is the remaining part, B, C, D, E. But B, C, D, E is in fact a list by this recursive definition because we can break down B, C, D, E into the head, which is B, and the tail, which is C, D, E, which in turn is a list because we could take the C out and we have the remaining part, the CE, or DE, pardon me, and then we have another list, E, right? The list containing the element E is a list with this recursive definition because it's got a head, which is E, followed by the tail, which is, well, in this case, the empty list. So we actually have a recursive definition of a list, which is pretty interesting. Any questions about this? What might be throwing you off a little bit on this one is how the list with one element in E has a head and a tail. But the tail is, well, an empty list in this particular scenario. I'm just giving you examples at this stage. Any other questions about what we're seeing here? I like questions. It gets boring if I don't get questions, so ask me questions. All right. So, repeating patterns. This is often, look, when we're dealing with recursion, we're dealing with repeating patterns in the same way that loops, we've got repeating patterns, okay? In the counting example, it may feel like cheating when I was saying like, oh, well, it's 1 plus however many are after the front. That may have felt rather silly, but let's go with it for a second. Because, and the reason it may feel silly is, like when I say, well, the total number of people in that list is 1 plus however many there are after the front. Because that's obviously not a concrete answer to the question. It feels like cheating. 1 plus however many are after the front. Because I know, like, however many are after the front, we're skipping a step. But we're not really, because we actually just like recursively applied that definition to get a concrete answer at some point. And if we don't get a concrete answer, we get like a Stack Overflow. But with this example, it was observed that repeatedly applying the same rule over and over on smaller and smaller lists, groups, lines of people, we were applying the same question to a very similar version of the problem. But notice that the version of the problem every time got smaller and smaller, right? We start with a big line of people, and the line got smaller by 1 every time. I'm going to give you an example of a recursive sorting algorithm. This is how it works, okay? And we're going to see this sorting algorithm by the end of the semester. So I'm going to jump ahead a couple of lectures. I'm going to show you this example because I think it highlights what I mean when I say, feels like I'm cheating. So here's part of a sorting algorithm called quicksort, okay? Imagine I have a list of unsorted numbers and I want to sort them. So here's how I'm going to do it. And this is actually a really efficient sorting algorithm, okay? I'm going to arbitrarily pick one of the numbers in this list. I'm going to hope that the number I pick is around the median value of all numbers in the list. But I'm just going to pick it at random, okay? So I'm going to pick some number. I'm going to put imagine I'm that number. Maybe I'm like 17, whatever, right? So I'm that number. And what I'm going to do is I'm also going to then go through that list of unsorted numbers. All of the numbers that are less than me, 17 in this example, I'm going to put in a list over here. They're not sorted in any way. I'm just going to put them into a bucket over here. And all of the numbers bigger than 17 are going to go over here. Do you understand where I am right now? So I have an unsorted list of all the numbers that I had that are less than 17, and an unsorted list of all the numbers that are bigger than 17 over here. And here's how we sort it. Here's the magic. Check this out. Here's what we do. Sort that list and sort that list. So now I have a sorted list of all the numbers less than 17. 17, I'll just tack myself onto the end of that one. And a sorted list of all the numbers that were greater than 17 over here, I just do that. And now I have a sorted list. Now you're scratching your head going like, but hold on. You can't just say, oh, just sort it. Because that's what we're doing. I'm describing a sorting algorithm to you. And I say, put all the numbers less over here, bigger over here, sort them, and just stick them back together. But you can't just say, go sort them, because that's what this is the sorting algorithm. But you want to know how you sort those things? You do the exact same thing again. You go to that list of all the numbers less than 17, you pick a pivot, you put all the numbers less than the pivot over here, bigger over here, you sort them. How do you do that? Oh, you pick a pivot, and you keep doing this. It's called quicksort. But doesn't it feel like we're skipping a step? Doesn't it feel like I'm cheating? Here's how we sort the list. Just sort it. What? But it's because we're going to apply the same sets of rules in the examples that we're going to see, the same sets of rules to the same version of the problem, to the same problem, but a slightly different, smaller version of it, a smaller instance of that problem. At any point when I'm talking, raise your hand if you have questions, because I know people get thrown off with recursion. You shouldn't be, but if you are, ask, because I want to make sure we're all on the same page as we go. Yes?
How would it know, so you have separate lists, right?
Yeah.
How would it know how to connect them together?
In the end?
Yeah.
Well, so in Python, for example, I could just add lists together, and it concatenates lists. Let's not worry too much about getting the nuance of that sorting algorithm, because we will get to the sorting algorithm. I don't want to get distracted by that. But if I had a list the list could be a size 100. If it's sorted, and this number is bigger than all the numbers in that list, I could just tack it on to the end, and I know I'm good to go. When I keep applying that quicksort, it's called quicksort. When I keep applying that, like pick a pivot, break the list. Pick a pivot, break the list. The lists are going to get smaller and smaller every time, right? Here's the trick of these sorting algorithms. If I have a list with one element in it, is it sorted?
Yes.
Yes. If I have a list with no elements in it, I'm not going to ask the question, is it sorted? I'm going to flip it. If I gave you a list and there's nothing in it, is anything out of order in that list? No. So a list with one thing in it and a list that's empty are intrinsically sorted as they are. So eventually, if I keep breaking these lists into smaller and smaller and smaller ones, eventually I'm going to end up with lists of size 1. And then I'm left in a position, oh, I have a list of size 1 over here that needs to be sorted. It's already sorted. So that's how we go down and then back up. It's actually quite spectacular. And this is quicksort. Quicksort's actually garbage. There's another one called merge sort, which is better, that works kind of along the same principle, but we'll learn these later. Other questions? That was a good question, though. Even though I didn't want to get into it, I kind of got into it a little bit, but that's fine. So, okay, repeating patterns. Okay. With the list example, it was observed that repeatedly applying the same rule over and over on smaller and smaller lists resulted in hitting an end, an empty list, which was the base case. The pattern arises a lot with recursion. Apply the same rules to the same problem, but a slightly different instance of that problem, right? Yeah. As mentioned earlier, there's typically a base case, kind of like this hard, clear definition of something, and then the recursive case, which is when something is defined in terms of itself. A list is an empty list or something with a head and a tail, right? So a list is an empty list, or a list is something with a head and a tail that is itself a list, which would have a head and a tail, which is the list, which would have a head and a tail, which is itself a list, and a head and a tail, which is itself a list. And eventually, hopefully, if it's not an infinitely length list, I'm going to hit an end. The looks on your faces are so hard to read. And when I say that, now you're laughing. What's so funny? Now the look on your face is different. All right. So going up and going down. So here we go, the set of natural numbers. Raise your hand if you know what a natural number is. Now, if you don't know what a natural number is, you actually do know what a natural number is. It's just 1, 2, 3, and so on. They're the natural numbers, okay? Arguably?
Well, whole numbers are the natural numbers. Sometimes people just pick either definition to be either one.
Yeah, but don't.
It's whether you include 0 or not, and whole numbers and natural numbers.
Whole numbers?
And I think
Yeah, but is there a whole number system?
Is natural numbers usually only start with 1 because that's when you start counting. That's where you usually start counting.
Yeah, but whole numbers, there's no whole number system, isn't there? Do you mean integers?
No, those include negatives. Whole numbers are just the natural numbers
Plus 0?
Yeah.
Plus 0. And you mean additionally with 0? Yeah. All right, fine. So it looks like here I'm saying 0 is a natural number, so deal with it. So 0 is a natural number. Okay? This right here, I'm going to describe the entirety of the natural number system with 2 lines. 0 is a natural number, and then a natural number plus 1 is also a natural number. And with this, you can conclude that what is also a natural number? Well, let's start with 1. 1. And that means if 1 is a natural number, what can you conclude is also a natural number? Nailed it. And if 2 is a natural number, what else? And so on and so on and so on. Look at this. We described an infinite series with 2 beautiful lines, right? How else are you going to describe? Good luck describing natural numbers in a more beautiful way. And I will say, too, a lot of programmers, myself included, find recursive definitions of things like aesthetically beautiful. There's something about recursive definitions that's just, it's got this really a beauty to it. And it's hard to explain, but I find it magical. So this recursive definition gives us an absolutely complete definition of the natural number system. One can start at the base case and repeatedly apply the recursive case to generate all natural numbers. You could generate them all with this rule. which I think is something maybe we should take a moment and reflect on. Like, with this recursive definition, it's just a series of, imagine, I don't know why I'm having a hard time thinking of a way to explain this right now, because I think it's actually, it's quite nice, so I want to make sure I'm explaining it well. Like, look, we could go list all of the natural numbers. We could do, well, actually, no, we can't, because it's an infinite series, but we could try. We could just keep going, right? We could do that. Think of the amount of books that would take up. A lot, in fact, an infinite amount. When I'm saying infinity, you know what I mean, right? Like, there's no end. Does anyone, can you prove that there's no, can you prove that there's an infinite number of numbers?
Yeah.
How?
Well, take any number.
Yeah.
Does that number plus 1 exist?
Yep. Nailed it. There you go. Very good. Let's suppose there exists the biggest number. Add 1. Oh, no. So I'm going to have to do that a lot. I'm going to need a lot of information to describe all of these natural numbers. Or I can generate them with these 2 lines. I can generate them with this, which is pretty cool. So the information can be generated. Instead of just existing, we can come up with rules that generate the information, which is pretty neat, right? I think that's something kind of worth reflecting on. So we can start at the base case and work our way up. Or we could actually just answer a question by saying, well, is 4 a natural number? We work our way down towards the base case to answer the question. Is 4 a natural number? Well, is 3 plus 1 a natural number? So, okay, well, is 2 plus 1 plus 1 a natural? Is 1 plus 1 plus, is 0 plus 1? Right, so I'm working my way down towards the natural number. Well, 0 is a natural number, and if 0 is a natural number, that means 1 is a natural number. If 1 is a natural number, that means 2 is a natural number. And if 2 is a natural number, then 3 is, and if 3 is, then 4 obviously is 2. So this is an example of like working backwards. Doesn't really matter. Obviously, it's kind of the same. It's just, you know, up and down, whatever. Questions, 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 questions. I know I said this last time, but whether you like it or not, you already are all really familiar with recursion. You use this type of, you use like recursion in your everyday life when just operating your surroundings, whether you like it or not. You just haven't thought of it in a systematic way before, like in a very explicit, formal, systematic way. So this is a lot of talk, but let's start programming things. So factorial. Raise your hand if you know what factorial means. At this stage, I hope you do, because I'm pretty sure I talked about it a bunch. But if not, it just means, so n factorial of a non-negative integer is the product of all non-negative integers between n and 1 inclusively. So it also includes 0, but we'll address this below. So first of all, n factorial is just a really succinct way to say, well, that just means n times n minus 1 times n minus 2 times da-da-da-da-da-da. Right? So 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Yeah? That's factorial. But we could define this recursively very beautifully. N factorial is 1 if n is 0. It's 1. That's it. Why? Because it's defined like that. Why? Because it is. If n is not 0, well, then it's just n multiplied by n minus 1 factorial. Because notice that 6 factorial is just 6 times 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. But that was just 5 factorial. 6 times 5 factorial. So we could define factorial recursively very beautifully. Now, as a note, for those of you that are curious, why is 0 factorial 1? That doesn't make any sense. Actually, it makes perfect sense. Because with operators, like when we're doing like addition, we'll have like an identity value for like addition. Like what is the identity? Like if I wanted a number and I wanted to add something to it such that the result was the number unchanged, what do I add to it? 0, right? And subtraction's like the same. What do I take away from a number to leave the number alone? You take away nothing. So like 0 works like that for like addition, but 1 works like that for multiplication. What do you multiply a value by to leave it alone? 1, right? So we're talking about multiplication here. So first of all, why is it? Well, first and foremost, it is by definition, so deal with it. Also, 1 is the multiplicative identity, and it is used as the result when applying no factors. This is just like how adding nothing, like I just said. It also aligns with the gamma function, which we're not going to get into, but anyways.
Also for permutations.
Pardon?
Permutations.
Sorry?
For permutations.
What about them?
How many ways can I pick 0 items from 0 items?
Yep. There you go. Beautiful. So if I ask you what 4 factorial is, well, 4 factorial is 4 times 3 factorial. All right, so what's 3 factorial? Well, 3 factorial is just 3 times 2 factorial. Well, what's 2 factorial? Well, 2 factorial is just 2 times 1 factorial. What's 1 factorial? Well, that's 1 times 0 factorial. What's 0 factorial? 1. Why? Because it said so. So if 0 factorial is 1, that means 1 factorial is just 1, which means 2 factorial is 2, which means 3 factorial is 6, which means 4 factorial is 24. See how I started with the question, what's 4 factorial? I worked my way down. I asked the exact same question again, but on a different version of the same problem. What's 4 factorial? Well, that's what's 3 factorial. What's 2 factorial, 1 factorial, 0 factorial? I kept asking the same question. I got an answer, and then I could propagate that answer back. Questions? This means everyone's A-okay and absolutely happy with everything, yeah? So here it is in code. Well, here's iterative factorial in code. Here's how you can calculate factorial with a for loop. Mind where the for loop's starting and ending, right? Just to make it it's a little cleaner. But iterative factorial takes an integer. This is a function that tells me the value of the factorial, right? Right? Takes some integer and it does the calculations, it returns the factorial. There's nothing particularly complex about that code, right? It's a function, it's got some variable, and it has a for loop in it, right? There's nothing bad about this. But here it is recursively. And it might be hard to get an appreciation for what I mean when I said like the aesthetics of a recursive algorithm on this example, because both are relatively small, but maybe you can kind of see what I mean. There's the recursive version of that code. First and foremost, if you're thinking to yourself, well, hold up, we're defining the function recursive factorial, and within recursive factorial on line 5, we're calling the method recursive factorial. Can you do that? Yes. It's entirely fine. A method can call itself. That's the recursive part of the definition. In fact, this code here is like it's one-to-one with the definition, like the mathematical notation definition of factorial. If it's 0, return 1. If it's not 0, return n times whatever recursive factorial of n minus 1 is. It's the same. And I find that code. How many variables even exist in this code? Just the argument, right? Just the parameter. And I'm not changing that value. The other one, it's stateful, right? We've got this factorial. We're updating it every time. There's nothing wrong with states, but we got rid of the states. I don't know. There's something, to me, there's like a beauty to this. Both the iterative and recursive do exactly the same thing. And when you consider the call stack, remember we talked about the call stack last topic? Every time we call a new method, we create a new data frame that gets pushed on the stack. So think about that stack, right? If I call recursive factorial 4, it's going to put recursive factorial 4, and then push recursive factorial 3, 2, 1, 0, and then 0 returns the value 1, and then we pop off the values from that call stack. So when we're using recursion here, we're actually making use of a stack, not a programmed stack. There's no stack data structure I've created. We're using the actual call stack, the system stack that your computer uses to manage the programs and everything. So it would look like this, for example. Any questions about what we're seeing here? Because now we've gone from okay, we talked about the idea of what recursion is, and now we're showing you some concrete example with code, factorial. So some observations. Notice how recursive factorial 4 makes a call to recursive factorial 3. If recursive factorial 5 was called, it would need to call recursive factorial 4 again. In other words, to know recursive factorial x in answer to x minus 1, x minus 2, all of these must also be calculated. They must be. At some point, they must be answered. One may also notice the similarity between the stack and the stack. Yeah, the abstract data type versus the actual call stack. And anything that can be done with iteration can be done with recursion and vice versa. However, just because it can doesn't mean it should. Here's the big asterisk with recursion. And then I'm going to have another asterisk that goes along with this asterisk. The first asterisk is because of how your computers work, and mine too, recursion is slower. Doing the exact same algorithm, iteratively versus recursively, it's slower with recursion. It actually is. You could time it, it'll be slower. But the second asterisk is, it really is just because of how these computers work. There's nothing about our universe that makes recursion slower. There's nothing about our reality that makes it just like an actually intrinsically slower process. It's the overhead of your computer jumping around RAM, creating call frames, pushing it on the stack, jumping around from where we are in the memory and then going back, return. All of that extra overhead, that's where the slowness comes. Now there's a third asterisk actually. Interestingly enough, Java is actually a really special programming language. Not all programming languages do this. In fact, I know Python doesn't. I don't know if C does. Maybe if some of the more optimized versions of C, C++. I don't actually know. But I know Python doesn't. Java's compiler does something called tail-end recursion optimization. Meaning, depending on how your recursive call is, how your recursion is written, Java will take your recursive algorithm. It won't change your code. But when it compiles it, it'll compile it as if you made an iterative version. So it actually won't be slower, which is pretty cool. So Java's recursion optimization is actually phenomenal. Python doesn't do that, which is too bad. But anyways, pretty neat either way. So that means that you can write sometimes code that's recursive is just so much nicer than iterative, but we know it's slower, so we don't do it. But we could get away with doing the recursive one in code, even because we know it'll get compiled to the iterative one, which will be faster. So the takeaway of what I'm saying right now is, in practice, on your computers, iterative processes are going to probably be a little faster. I mean, we're going to be talking about like tiny amounts of time, but they will be faster. But that's not because recursion is actually a slower process. It's your machine's fault, not recursion's fault. Clear? Yeah, cool. Yeah, so just based on how the computer systems work, recursion creates a lot of additional overhead, creating call frames, pushing and popping from the stack, tail end optimization. That also doesn't mean that one should not use recursion, though. In fact, you actually really should use recursion in some instances because code explainability, sometimes recursive algorithm is just so much nicer. Yeah, and performance is always a later thing. Because to me, again, this is a small example, but in my opinion, everyone who knows what factorial is knows that factorial is defined that mathematically, right? With that big brace where, well, that is, let me show you. Everyone knows this is the mathematical definition of recursion. When you look at these two functions, static methods, sure they're both simple, sure they're both small. In my opinion, one of these two is so much cleaner, so much clearer. It's the recursive one. Because it's just the definition of factorial. It's clearer. The iterative one, I can make sense of it, but it's actually harder for me to make sense of the iterative one. I have to like figure it out. I look at that code, especially because I'm looking where I's starting and where it's ending, and I'm like, oh, what? It is more complex. And we will notice this a lot as we go, as our functions get more complex. The recursive ones tend to be pretty nice. Okay, the computers, we as humans, this is just what I was saying. It's not actually slower. Cool. One of the tricks we use, though, when analyzing our code in terms of computational complexity, what was the trick I told you? Go look at the loop. How many times is that loop going to run based on n? That was the trick, right? When we're looking at recursion, we still care about computational complexity. So now the trick of go look at the loop becomes a bit of a problem because there is no loop. But it's the same trick. It's how many times is this chunk of code going to run? And this is where we'll pick up tomorrow. Any last questions? All right, I'll see you later. Is anyone going anywhere near campus security? Yeah? Perfect.